Today we're going to continue in section 12.5. Remember, in the first part of this section we looked at our different shapes of our different distributions. So we looked at some different types of distributions, and then we kind of started to focus in on the end on our normal distribution. Remember, our normal distribution, or our normal curve, is a bell-shaped, unimodal, and symmetric about the mean. So that means that the shape of our graph is somewhat of a bell shape. Unimodal means there's one peak, one highest part in the center, and then that part is centered around the mean. So the mean is going to be the center of our data set. What we're going to look at in this next video is we're going to look at something called the empirical rule. Okay. So thinking about our normal curve, since the normal curve is symmetric, 50% of our data is always going to fall above the mean, and 50% of our data is always going to fall below the mean. So our mean is going to be the absolute center of our data set here. In addition to just thinking about our mean, we're going to use something called the empirical rule to categorize other data values within our distribution. So the empirical rule is a rough guideline for the approximate percentage of data within 1 to 3 standard deviations of the mean. So the empirical rule says that if the distribution is unimodal and symmetric, then approximately 68% of the observations will be within 1 standard deviation of the mean. Approximately 95% will be within 2 standard deviations of the mean, and approximately 99.7%, or nearly all of the data, will be within 3 standard deviations of the mean. We might see the word unusual in some of these problems that are coming up. We generally consider values to be unusual if they are further than 2 standard deviations from the mean. So to make our empirical rule kind of easier to understand, we're going to look at a visual representation of our empirical rule. Right, so in this top one, what we see here, this center value, this is our mean. And then as we go 1 standard deviation in either direction, notice that we then have 68% within this 1 standard deviation. We go an additional 1 standard deviation, well, that's 2 standard deviations in either direction. Right, that's going to tell us that there is 95% of our data between there. We go out to 3. Notice that at this point we've covered almost our entire curve. Right, we should have 99.7% of our data. Right, the other image below here just kind of breaks it down a little bit differently. Instead of just the 68% in the middle, we've got 34% and 34%, which total the 68%. Then as we move out in these next little pieces, we have 13.5% going in each direction, 2.35% as we move out into these tail pieces, and then there's just a very tiny portion that's not mentioned here that is going to be out in those far corners. Okay, so we are going to use this empirical rule to find out some different things about a particular distribution that we are looking at. So the mean daily high temperature in San Francisco is 65 degrees Fahrenheit, and the standard deviation is 8 degrees Fahrenheit. Use our empirical rule to determine the following temperature ranges. Right, so we want to first determine the values for 68% of the temperatures. So what we're going to do is we're going to take our mean, right, and we are going to subtract our standard deviation. So 65 minus 58 gives us 57. Then we're going to take our mean and we're going to add our standard deviation. 65 plus 8 gives us 73. So within 1 standard deviation in each direction, right, we have 68% of our data. Right, so between 57 and 73 degrees, we have 68% of our data. Right. Now as we go down to our 95%, we have a couple of different ways of calculating this. Right. So one thing that we can do, and generally the way, just to make it easier when we're figuring it out on a calculator, we're going to take our values that we had from the last group and we're going to add and subtract our standard deviation. So we're going to take 57 minus 8. That's going to give us our lower limit, which is going to be 2 standard deviations from our mean. That's going to be 49 degrees. Okay. And then we're going to take our 73 plus 8, which gives us 81. That's going to be our upper limit for our 95 degrees. Now our other option, if you don't want to take your values from your previous answer, we can always take 65, which was our original mean, minus 2 times our standard deviation. So 2 times 8 also gives us 49, and then 65 plus 2 times 8 also gives us the 81. So we have a couple of alternate ways of calculating these. It's up to you what you want to do. Right, then we're going to move out to 3 standard deviations. Right, so we are going to take, again, our answers from this last one. 49 minus 8 is going to give us 41. 81 plus 8 is going to give us 89. So we have 41 degrees to 89 degrees. Again, or our other option, go back to the beginning, take 65 minus 3 times our standard deviation. So 65 minus 24 also gives us 41. 65 plus 24 also gives us 89. Right, now what we're going to do is we're going to take these different values, right, and we're going to label our normal curve using these values. So we start with our middle value. Right? So our middle value here is going to be that temperature of 65. That was our mean. Right? And then as we go to the right, we're going to use these values down here. So we added 8, we got 73. We added 8 again, we got 81. We added 8 again, we got 89. Then we go back to 65, subtract 8 each time, we get 57 for the first one. Subtract 8 again, we get 49. Subtract 8 again, we get 41. Okay. So all of our values that we see up here match up with our labeling along our normal curve. As you're working through some of the homework problems, mini quiz problems, test problems, you want to kind of keep this in mind that it might be to your benefit to draw yourself, just kind of sketch out a basic normal curve, right, and then label these as we go. We're also going to use this idea in the last group of problems that we're going to work through in section 12.5. Right, so for example B, we're going to use this picture that we have. Using the empirical rule, decide whether it is unusual to have a day when the maximum temperature is colder than 48 degrees in San Francisco. Right, so we're going to use our diagram to help us answer this. Right, so if we look at this, 48 degrees. 48 degrees would land somewhere over here. Right, 48 degrees, right, we want to decide as far as the word unusual goes. Right, unusual means it is more than 2 standard deviations from the mean. Well, our cutoff for 2 standard deviations for the mean is that 49 and that 81. Right, that was that 95% that we have up here. So this value of 48 is outside of that range. So we are going to say yes, it would be unusual. Right. It is unusual, right, because it is more than 2 standard deviations from the mean. Another thing to kind of think about this idea of unusual. 2 standard deviations is 95%. So if we think about that, between these two values we have 95% of our data. That leaves 5% that's left over. That means that to this side and to this side, there's only 2.5% of our data on each side of that, which is the same thing that we would get if we add those 2 different values. Right? So we can also say only 2.5% of the days have a maximum temperature below 49 degrees Fahrenheit. Right? So when we're thinking about unusual, it means we land either to the 2.5% on this side or the 2.5% over on the other side. Our next example asks us to calculate some different values. So heights for females that are the same age are normally distributed. In a random sample of 500 females, determine the approximate number of females in the sample who are to have a height within 1 standard deviation of the mean and within 2 standard deviations of the mean. So thinking about this, we're going to go back and think about our percent formula. Our percent formula says percent times whole equals part. So we're going to use that idea for both of these next two questions. So as we work through these, within 1 standard deviation of the mean, remember, is 68%. So we're going to take 68% times our sample size, which is 500. So we should expect that 340 females, which is 68%, fall within 1 standard deviation of the mean. Within 2 standard deviations, 95% times 500 gives us 475 females. So there we can also see that this 95%, if we're outside of this 900 or this 95%, we're outside of this 475 out of 500. Anybody that's in either direction, either way, would be considered unusual. So you are going to run into a couple of questions as you're going through homework asking you to do these types of calculations. Just remember, just think about our percent formula that we saw originally all the way back in chapter 10. The other thing we're going to start talking about in this second section of 12.5 is we're going to talk about our z-scores. Z-scores are going to be a way that we are going to measure how far away we are from our mean, how far away we are from our average or our central tendency in this case, which is our mean. So to start with, our first definition is that of standard units. Standard units measure value relative to the sample rather than with respect to some absolute measure. So what this means is we're not necessarily going to have to worry about labels when we're talking about standard units. Standard units, we're going to refer to how many standard deviations we are away. So we're not going to have a label, we're just going to have a number. A measurement that is converted to a standard unit is called a z-score. And that is what we are going to use for the rest of the section, which is going to tell us exactly how many standard deviations an observation is away from the mean. As we're working with our z-scores, it can tell us different things. If our z-score is that of the mean, it's going to be exactly 0, because that's going to be our exact middle point. A positive z-score is going to mean that our observed data value is greater than the mean, so we're to the right of the mean. A negative z-score shows the observed value is less than the mean. So if we look at this picture and we kind of think about this in context, this value of 70, even without reading the paragraph that's over here, this value of 70, that's our mean. That's our z-score of 0. Anything to the right of this, is a positive z-score. Our z-scores range from between 0 to 1 to 2 to 3. Anything to the left, -1, -2, -3. So that gives us an idea, thinking about z-scores, of where our values are going to land in this distribution. So a man who is 73 inches tall. So if we look at this, a man who is 73 inches tall would have a z-score of 1 standard unit. It is exactly 1 standard deviation away from the mean. A man who is 64 inches tall would have a z-score that is -2. So 64 corresponds to a z-score of -2. How many men would have z-scores greater than 2? Well, greater than 2 would simply be these two values that are out here. So there would be 2 men that would have z-scores that are greater than that value of 2. So our z-scores, they tell us a lot. They tell us, are we above the mean? Are we below the mean? How far away from the mean actually are we? So in context, z-scores enable us to compare observations in one group. We can also use z-scores to compare observations in 2 different groups. So that's the other nice thing about z-scores. Right? So even if they are measured in different units or under different conditions. Right, now the question is, well, what happens if we didn't have a male in this distribution that was exactly at 61, 64, 67, 70, 73, 76, or 78? Right? How do we calculate, for instance, somebody who was 72 inches tall? Right? What z-score would they have? So down at the bottom of the page, we have a formula for calculating those z-scores. So to find the z-score, we're going to find the difference of the observed value and the mean, and divide that by our standard deviation. Our observed value always comes first. So whatever value is in question, that's always going to be our first value. In this particular case, we used our notation for populations. So instead of using X bar as we did and S in other sections, in this particular formula, we use mu and sigma, but it means the exact same thing. So our X is our observed value, our mu or X bar is our mean, and then our sigma or our standard deviation that we're dividing by, that is going to be our denominator. So we can use our sigma or our S. So suppose road A had a mean speed of 60 miles per hour with a standard deviation of 5 miles per hour. That should be a letter A, not a letter S. Road B has a mean speed of 60 miles per hour with a standard deviation of 10 miles per hour. Suppose a driver travels 75 miles per hour on each road. Calculate the z-score for each different road. All right, so our first road. So the observed value, this driver is going 70 miles per hour. Right, and on road A has a mean speed of 60. So we're going to subtract 60. Again, it's always our observed value minus our mean. And then we're going to divide it by our standard deviation. Our standard deviation on road A is 5. So 10 divided by 5 gives us a z-score of 2. Right, now on road B, same driver also going 70 miles per hour. Right, road B has a mean speed of 60. So our numerator hasn't changed. We're still 70 minus 60. But our standard deviation is 10. So we're going to divide this by 10. So we get 10 over 10, which is 1. So the nice thing about z-scores, it gives us a comparison to the mean, and we can also use z-scores to help us compare values from different data sets. Right, so looking at these two different values, our z-score on row A is higher than it is on road B. So is a driver going 70 miles per hour on road A traveling relatively faster or slower than one on road B? So we will say, since the z-score on road A is higher, the driver is traveling relatively faster than a driver at the same speed on road B. So we can use our z-values to make comparisons. Again, we can also use our z-values to answer the question of whether or not something is unusual. In the last part of section 12.5, we are going to take a closer look at our normal curve and our z-scores and use these to find some different probabilities as well, which is the normal probabilities are referenced on the bottom of this page, and we will continue here in the next video.